Hey guys, so here's my baby, Claire. Yeah, she's pretty cute, lots of hair. Claire with the hair. Yeah, so I decided to make a video for you guys to try and help you out with the physics assignment. Sounded like some of you were having some troubles, so hopefully this helps. I want to take a look at the practice problem number 3. It seemed like that was a difficult one to do, so I'm going to walk you through it and give you some tips as we go along. So just turning your textbook there, practice problem number 3. So it says that a ball rolls at a velocity of 3.5 meters per second toward a 5 kilogram ball that's at rest. They collide and they move off at a velocity of 2.5 meters per second. What was the mass of the moving ball? Okay, so when you're dealing with problems that involve collisions, this is something that I didn't get to teach you on Friday because I had to leave or class was over. But this is really important. When you deal with problems that involve collisions, it's really important to identify the type of collision that you have. You'll remember that we looked at collisions that were elastic. That's when the objects smash into each other and they don't stick together. They bounce off each other. That's what's called elastic. And then there's inelastic collisions where the two objects collide and they somehow get stuck together. So in this example, we've got one ball that's moving towards another ball that's not. When they collide, and it says they move off at a velocity of 2.5 meters per second, because they only give us that one single velocity, it's a little vague in the grammar, but we can assume that those two objects were somehow stuck together. Okay, so these balls are somehow sticky, or I don't know. But they collide and they move off together at a single velocity, which tells us that this is an inelastic collision. Okay, they stick together. So that's the first important thing, is you need to identify the type of collision. The next thing you need to do, and this is really important with momentum problems, you kind of do it instinctively with all physics problems, but with momentum problems it helps to remind yourself of this. You need to identify your frame of reference. Okay, so I'm just going to use the standard up is positive and right is positive and down and left are negative. So when it says that the first ball is moving at 3.5 meters per second, I'm going to say, alright, that means that that ball is moving to the right. Okay, and then when they both move off at a velocity of 2.5 meters per second, again, I'm assuming that they're moving off to the right. Okay, so identify the type of collision that you have and identify your frame of reference. Now we're set up to solve the problem. So the law of conservation of momentum tells me that the momentum of the system before and after the collision must remain the same. Okay, I'll say that one more time because that's really the most important thing about all of this. The momentum in a system, okay, so in this case the momentum in this collision is the same before the collision as it is after. Okay, so we say P before equals P after. Alright, so based on that, let's look at the momentum before the collision happened. Okay, well, before the collision happened, I had mass 1, that's the ball that's moving, we'll call that mass 1. Moving at a velocity, we'll call it V1. There was a second ball we'll call it mass 2. It was the 5 kilogram ball, and that's at rest. So we'll call its velocity, even though it'll be 0, we'll call it V2. Alright, so the left-hand side of that equation is the momentum before the collision. Now what happened after? Well, they got stuck together and they moved off at a single velocity. So I'm going to add their masses together, m1 and m2, to treat it like a unified singular object moving at a specific velocity. Okay, so I add their masses together because they got stuck together and now they're just moving at the same speed, right? So I'll just call it v. Alright, so we put in our numbers. The moving ball, the one moving at 3.5 meters per second, we don't know what its mass is, but we do know its velocity. So we leave the mass as m1, and we write the velocity as 3.5, like they told us. The second object has a mass of 5 kilograms. but it's not moving, so its velocity is 0. So that's the left-hand side. The right-hand side, the two objects are glued together, so I'm going to add their masses. Again, since I don't know what the first object's mass is, I keep it as m1. But I do know the second objects, so I just replace the m2 with 5. And then all of that will be multiplied by the velocity of the entire thing, 2.5. Alright, so just doing a little bit of simplifying, the first term becomes 3.5 times m1. The second term becomes 0. It has no momentum, right? When something is just sitting there, it's got 0 momentum. Equals the right-hand side. Now what I did there is I distributed the 2.5 to the m1 and the 5. So 2.5 times m1 is 2.5 m1, and 2.5 times 5 is 12.5. Then I want to solve for m1, so I bring the 2.5 m1 from the right-hand side to the left-hand side, and when you change sides you have to change signs, so I subtract, and 3.5 minus 2.5 is just 1, or m1, so we don't really have to do any dividing. That's nice. So the mass of the first object is 12.5 kilograms. And actually looking at it now, I got the significant digits wrong. That should be 13 kilograms because we had two significant digits. Okay, so I just want to again point out some important things in this problem, especially when you're dealing with collisions. First, identify the type of collision. Are the objects sticking together or are they not? Secondly, set up your frame of reference. Decide what is positive, what is negative. I mean, we could have switched this. We could have made up negative and right negative. It's kind of weird, but we still would have gotten the right answer. But I just used the more standard convention. And then thirdly, remember that the momentum of the collision just before the collision happened and just after is the same. The momentum is conserved before the collision and after. Obviously, after the collision happens, the objects won't keep moving at that speed forever. They'll, transfer their energy into friction and sound and heat and all these sorts of things. But the moment before the collision and the moment after the collision, the momentum of that system is conserved. Okay, so I hope that helps. I wanted to also do a problem like number 3 in the review questions. This is a good momentum problem. I just make up a problem for it because there isn't really anything in the notes or in the examples that is like this problem. So I wanted to do an example to give you a little bit of help. Okay, so I just changed some of the numbers, but it's pretty much the same thing. So you have a 0.05 kilogram rifle bullet leaving the muzzle of a gun with a velocity of 580 meters per second. If the 3.2 kilogram rifle is held very loosely, what velocity will it recoil? Okay, so I'm basically just shooting a gun and trying to figure out how fast the gun wants to move immediately after the bullet is shot out of it. If you've ever shot a gun before, you can feel that impact in your shoulder or in your hand when you fire the gun, right? And if you don't hold on to it very tightly, it'll knock you in the face. Okay, so this isn't necessarily a collision problem. It kind of is because the firing pin hits the bullet, which causes the explosion, which causes the bullet to fly out of the gun. So you could think about it like that. But I'm not going to take that route. If it helps you think about it like that, then you can do that. But I'm going to try to explain it a different way. Again, it's important to set up your frame of reference. So I'm going to say up is positive, as well as right, and down and left are negative. So in this example, the bullet, you can see, has a positive 580 meters per second velocity. That means I'm assuming that the bullet is moving to the right. Okay, that's important, because if you think about shooting the gun, the bullet will travel to the right. Which way is the gun going to go? Well, the gun obviously going to go in the opposite direction. It'll fly to the left. So we should notice that the velocity of the gun in the end is negative, right? So watch out for that. Alright, so we set up our frame of reference, and then we say, alright, the law of conservation of momentum tells me that the momentum of the system before and after must be the same. So in this case, just imagine the bullet sitting in the gun stationary, okay, and the guy shooting the gun, is aiming at his target, and before he pulls that trigger, the momentum of the bullet and the gun is zero, essentially, right? The gun isn't moving, the bullet isn't moving, it's zero, okay? After the bullet is fired, okay, this would be the momentum of the system after, the bullet will fly to the right, the gun will fly to the left, but their momentums should still cancel each other, right? If I were to take the momentum of the bullet and subtract the momentum of the gun, I should get zero, because before the bullet was fired, the momentum of that system was zero. So keep that in mind as well. Alright, so I used B to represent the bullet and R to represent the rifle. The mass of the bullet plus the mass of the rifle times velocity. That's before the bullet is fired. Now remember that the bullet and the rifle are still one, right? The bullet is inside the gun, so it hasn't fired yet. So I'm going to add their masses together and multiply it by singular velocity because they're the same thing right now. After the bullet gets fired, now they're two separate objects, so I have to consider their momentums individually because they're two separate things now. So before the gun is fired, I add the momentums. The velocity is zero, right? Because it's not moving. The guy's just getting ready to fire. Afterwards, however, the bullet, 0.05 kilograms, moves at a velocity again to the right of 580 meters per second, and I add that to the mass of the rifle, 3.2 times its velocity r, which I'm going to solve for. So, again, if I multiply all that stuff on the left by 0, because it's not moving, its momentum is 0. Okay? And that gives me, doing some calculations on the right, 0.05 times 580 is 29, and then 3.2 VR just stays the same. Bring the 29 over, it becomes a negative, divide both sides by 3.2, and I get the velocity of the rifle to be negative 9.1 meters per second. Okay, so like I mentioned before, because the bullet is flying out to the right and it causes recoil in the gun's going to want to go to the left. So if the velocity of the bullet is positive, going to the right, then the velocity of the rifle has to be negative. And maybe it would be good for you to just convince yourself that the momentums of those two objects are equal and opposite. Right? Just calculate the momentum of the bullet. Right? Just go 0.05 times 580. And then calculate the velocity of the rifle. Go 3.2 times negative 9.1. You should notice that they are the exact same numerical value. It's just one is positive and one is negative. And the reason why is because their momentums have to cancel each other out in order to be equal to the momentum that we had before the gun was fired. Right? They have to cancel out to equal 0 because that's what our momentum was before the gun was fired. So I hope this helps you guys. Again, give it your best shot, and yeah, I guess we'll see how you did once I get back. Okay, have fun.